part 4 now of the lecture on 16.7, and I've got a longer problem to work, and one thing that's a little longer about it and the whole part of the lecture is that we need some warm up, and I need to say a few things before we actually start doing that problem. The first thing is a definition of a couple of terms. For a closed surface, such as a sphere, the outward orientation is said to be positive. And the inward orientation is said to be negative. So if you've got a sphere and you're asking yourself how much of the vector field is moving from inside to outside the sphere, you're calculating the positive flux across the surface. If you're asking how much of the flow is going from outside in, you're calculating the flux with respect to the negative orientation. So positive orientation, negative orientation. Okay, also I want to say a little bit about an important special case. So suppose that S is a surface which is parallel to the XY plane. So S is part of a plane. So, and it doesn't have to be above the XY plane, but could be. So S is above in this instance and parallel to the XY plane. Then, of course, S is given by a function of X and Y. So X and Y are parameters. And G of XY, which gives Z, is just some constant C. Then this term in the double integral, we're looking at the double integral of f dot n ds, and you can see immediately what the normal vector here is. For upwards orientation, n is just equal to k. For downward orientation, n is negative k. That's because of the being parallel to the XY plane. But then the question is, what is this ds? And ds, the differential of surface area here, is just the magnitude of r sub x cross r sub y, which I guess I probably shouldn't even write it like that. It's really, we've already looked at this. It's the square root of z sub x squared plus z sub y squared plus 1. ds is this, really, dA. And so this, see the partial of z with respect to x and the partial of z with respect to y, they're both 0. So this is just square root of 1 dA, or in other words, dA, which totally makes sense. This differential of surface area here is just the plain old dA. This is just the XY plane, moved up. So my point in saying this is, if you're ever integrating across a surface which is parallel to one of the coordinate planes, then you don't have to go through all of this. You can just always see what your n is. This would be the same if we had a plane out here parallel to the YZ plane. Given the orientation, you can see whether your normal vector is this way or this way, and of course it's just going to be, in this case, either I or negative I for unit normal. So you can just go directly to f dot n, just compute f dot n, and in these cases ds is just dA, and you don't have to worry about all the cross products. So that's the point there. So, all right. Well, with that as background, and if I did confuse you there, you're about to see it in this next problem. So let's actually, maybe I'll make use of this paper here. Let F be the vector field x squared, y squared, z squared. And let S be the boundary of the solid half cylinder given by 0 less than or equal to z less than or equal to the square root of 1 minus y squared, for 0 less than or equal to x less than or equal to 2. And let's find the flux of F across S, where S has positive, in other words, outward orientation. I'll do my best. Whoops. Do my best to draw this. So X, Y, and Z. Okay, so what is this? The work is done here for the equality between between these two expressions. So that's z equals square root of 1 minus y squared. Square both sides, and you get, y squared plus z squared equals 1. So y squared plus z squared equals 1, that's a cylinder. But this says half cylinder. So, okay, it's the half cylinder where z is non-negative. So that's just the part above the xy plane, of course. So the half cylinder would be this half circular cylinder, but we only want the part between 0 and 2. So I'll just estimate and draw something out here. So from 0 out to 2. And then I need to sketch some sort of a half cylinder, and this is where I need 3-dimensional abilities, which I don't have. Let's see. All right. Yeah, that's good enough. Just draw a little few. So we've got this half cylinder here. Now notice we're told that this is the solid half cylinder. Z is non-negative. X only goes 0 to 2. So see, 0 equals x, x equals 2, 0 equals z. These are all planes. So the plane x equals 0, that's the yz plane. So that's telling us that, this face here is a boundary of the half cylinder, or part of the half cylinder that we're looking at. So we've got the part that really looks like it's part of the cylinder. We've got an end here. We've got another end here. And then, I guess if I can draw it or shade it in, we've got the bottom. So there's four sides to this, 4 surfaces. We're going to have to compute the outward flux of F across each of these surfaces. So let's call the top, the part that looks like a circular cylinder, S1. There's no real sort of right or wrong way to label these, of course. S2, S3, and S4. And outward means, outward is going to mean we've got one direction here. So here, the outward direction is going to be in the positive, towards the positive x-axis, normal to this surface. From this surface over here, S4, outward is in the negative x direction. So you just have to take it one at a time, look at the picture, and so this is, the reason I talked about flat surfaces, we've got 3 flat surfaces here that we're going to compute the flux across. So let's actually do those flat surfaces first, and then save S1 for last. It's a little bit more work there. So, all right. So let's start with S4. And you always just need to start by characterizing this surface as, a function of 2 parameters, characterize the normal vector. So here for S1, since S1 is on the XY plane and the solid is above the XY plane, outward is down. So in this case, N is, let's see, I'm sorry. S4 is this side over here. So I'm sorry. I wrote S4 and then I started looking up here. Let's actually do S4. So scratch the past few seconds. S4 is outward normal for S4 is minus I. So in other words, -1, 0, 0. And S4 is parallel to, and actually part of, the YZ plane. So here we would think of Y and Z as being parameters, and then X, which is a constant, is 0. And really we're thinking of this as the function of Y and Z. So then we're looking for F of G of Y, Z, Y, and Z. So that's 0, and then Y squared and Z squared. So we've got F, we've got N. What is F dot N here? F dot N is 0, Y squared, Z squared, dot -1, 0, 0, which is a zero burger? Is that what the nothing burger is the phrase, I guess. This is 0, right? 0 plus 0 plus 0. So no need to be too fancy with it. Just say that the double integral for the surface S4 of F dot N ds is equal to 0. Once you get that you're integrating 0, just be done with it. Okay. Now let's keep going here. Let's see, here's my, we did S4. Let's do S3. So for S3, our normal vector is now I, 1, 0, 0. And S3 is again parallel to the YZ plane. So Y and Z are the parameters. This time, however, X is equal to 2. And so F of X as a function of Y and Z, and then Y and Z is, so remember, the original function is X squared. So when I'm plugging X of Y of Z into X squared, that gives me 4. Then Y and Z are just Y squared and Z squared. And now F dot N is 4 plus 0 plus 0, which is 4. So then we need to integrate 4 over this region here. Well, I guess I would be inclined to go polar, because really we're integrating over the region which is in the YZ plane. See, we're just integrating over a circle. So really we're saying, you know, y equals cosine theta, z equals sine theta. And it's just polar coordinates with respect to the YZ system. So this region here is r goes 0 to 1, and theta goes 0 to pi. So this is 0 to pi, 0 to 1, 4 times r dr d theta. The d theta integral is just pi. So the 4 comes out, we get 4 pi. Then the r is r squared over 2 from 0 to 1. And this all gives us 2 pi. All right. So we've got our integral over S3 gives 2 pi. The integral over S4 gave us 0. Now let's do S2. On S2, we are in the XY plane. So X, Y are the parameters. Z is a function of X and Y, and it's identically 0. As I said earlier, when I got ahead of myself a little bit, our normal vector here is now downward orientation. So minus k, which is 0, 0, negative 1. F here becomes x squared, y squared, and then 0. And then f dot n is 0 plus 0 plus 0. So 0. Double integral S2 of f dot n ds is just 0. All right, now for the fun part, what I label it S1. For S1, we're not a flat surface. We are the curved part of the cylinder here. And it's given by this function here. So for S1, still though, this is a function of x and y. So x, y are parameters. G of x, y is the square root of 1 minus y squared. And I won't be too tedious. We can tell that 0 is less than or equal to x less than or equal to 2. That part was given. Since this is the equation of a unit circle in the YZ plane, you can tell that y has to go between -1 and 1. Okay, and we want upward orientation here. So upward orientation is n equal to minus g sub x minus g sub y k. Oops, I'm sorry, 1. Get rid of that. Don't want to put k, a vector, inside the vector notation. So 1 there. And then, of course, partial g with respect to x is equal to 0. I'll let you, if you need to, fill in the details, but partial of g with respect to y is minus y over the square root of 1 minus y squared. So then n is 0 minus y over the square root. Let's see. Sorry. No, we don't want the minus because I want minus g sub y. G sub y already has the minus in it, minus sign. So y over square root of 1 minus y squared. And then 1. And I haven't stated f yet. F as a function of x, y, g of x, y is x squared, y squared, and then g of x, y. See, really, we have z squared here, but z, I should have said that here, g of x, y is what's giving us z here. So z squared is the square of that, so it's just 1 minus y squared. All right. And we now can set this up as a double integral over the region in the xy plane. We've got, let's see, I'll do minus 1 to 1 first, 0 to 2. So I'll do the dy integral first. This is f dot n is 0 plus y cubed over square root of 1 minus y squared plus, okay, so then y cubed over square root of 1 minus y squared plus 1 minus y squared. And then I'm doing the dy integral and then the dx integral. And I know you wouldn't think of this right off the bat, or at least I'm guessing you wouldn't, because the only reason I think of it is because I've taught out of Stewart a bunch of times. But this first function of y here goes from minus 1 to 1, and it's an odd function. So h of y equal to y cubed over square root of 1 minus y squared is odd. It integrates to 0 over any interval from minus a to a, as long as it's defined there. Oh. But is it? I'm going to have to come back. This is an improper integral, isn't it? And I don't remember addressing that. I'm going to push pause really quick here. Okay, so when I originally worked this problem, I said to myself, well, this is an odd function, and odd functions over things like minus a to a, integrate to 0, at that point it occurred to me that for this minus a and a, the function that we've got is discontinuous at the endpoints, okay? If you plug -1 in, you've got, of course, 1 on the top, but on the bottom, you've got square root of 1 minus 1 squared, or, in other words, square root of 0. So this function is discontinuous at the endpoints. So we cannot use the argument about symmetry because that's a balancing out argument. You actually have to, in order to evaluate this integral from -1 to 1 of y cubed over the square root of 1 minus y squared dy, to do this outright, you have to rewrite this as the integral from -1 to 0 of y cubed over the square root of 1 minus y squared dy, plus the integral from 0 to 1 of y cubed over the square root of 1 minus y squared dy. And then evaluate each of these either by using table of integrals or substitution. The substitution that works, I think, most easily is u equals 1 minus y squared, du is minus 2y dy. You then split this y squared, y cubed up. Part of your y cubed goes over here. But then part of it stays y squared, and you can solve this substitution formula. Y squared is 1 minus u. So so you pull this over into the du, and you pull this over and you make this 1 minus u. In any case, for this one, after you do all that, it's really the limit as t goes to -1 from the right of the integral t to 0 of, all of this square root of 1 minus y squared dy. But quite honestly, I don't want to go into all of that. I'm just going to leave that for you as a practice problem. It integrates to 0. So and as far as I can tell, there's an error in Stewart's answer manual because he doesn't catch this. He doesn't actually treat this like an improper integral. So I'll have to see if he's made that correction in future editions, and if he hasn't, I'll let the publishers know. Stewart himself is no longer with us. But okay, so all the way back up here, it can be shown that this part integrates to 0. So then the whole rest of it is, let's see, what do I want to do? Integral from 0 to 2 minus 1 to 1 of just the 1 minus y squared. So it's integral from 0 to 2, integral minus 1 to 1 of 1 minus y squared dy dx, which is the integral from 0 to 2 of y minus y cubed over 3 from minus 1 to 1 dx, which is the integral from 0 to 2 of 1 minus a third minus, and then minus 1 minus a third dx. This is the integral from 0 to 2 of 4/3 dx, which is 8/3. Okay, so then the outward flux of F across S equal to S1 union S2 union S3 union S4 is, let's see, get these right, order. We just did S1 is, so that's 8/3. S2 was a 0. S4 was a 0, and so S3 was the 2 pi, and the final answer is 2 pi plus 8/3. Well, if I decide to say any more about that one integral that got a little tricky, I'll follow up on it in a later lecture.